Am I audible?
Yes, sir.
Okay. So let it wait for 2-3 minutes and then we will start the class. Rest of all can join in that between. Okay, so let us start the class. Good morning, everybody. Hello. Yeah.
Yes,
Yeah.
sir.
Good afternoon, sir.
Can you hear me?
Sir.
Am I audible?
Yes,
Sir,
sir.
yes, sir.
So I am sharing the whiteboard. Is J. Can you hear me now?
Yes, sir.
Okay.
Yes, sir.
Okay. Okay. So the last class, what we have taught about the. If we see our last class lectures, we will see. Just a minute. I am sharing the last class lecture. In that is the we have discussed about the expression of collector current. We discussed about the current amplification factor and its relation. Then we do some numericals using the alpha and beta value. Would you remember that thing? So today we will start from there. We will discuss about the transistor configuration in CBC and CC mode. And we will do what? We will do the VI characteristics of the volt ampere characteristics of this transistor biasing. So let us start with the transistor characteristics and transistor characteristics in common base configuration. So you are audible, everybody can hear me?
Sir,
Okay, so everybody please focus on this uh, whiteboard. Today is our 21st February 2022. So in our transistor characteristics, that is common base mode, let us see what is our common base mode circuit. Okay. So let us give you the actual, just a minute, let me see you. Just a minute, giving a second. If you will see this, I'm sharing, closing the word, right? Sharing the screen. So you can see here. So this is the circuit configuration, or you can tell this is the circuit configuration for transistor characteristics in common base configuration. Okay. So can you see the figure?
Yes, sir.
Okay. So in common base configuration, two types of characteristics we will see. One is called the input characteristics, another is called the output characteristics. So what is input characteristics? Input characteristics curves relate the input of the emitter current IE and the input of the emitter to base voltage VEB, keeping output or collector to base voltage VCB constant. So that is called the input characteristics curve. And for the output characteristics, it relate the output or collector current IC and output or collector to base voltage VCB, keeping the input of the emitter current IE constant. Understand this? So let me see you elaborately. I am stopping this share, and again I am going to the whiteboard, and I will see you the diagram what I told. So this is the transistor. Okay. This is the base current. This is the flowing of the base current. This is, we are connecting a variable resistance here. This is the voltage V. This is VEE. This is minus, this is plus. This is R1, the resistance. This is RS. Here I connected user. Here I connected a ammeter A. This is minus, this is plus. This is minus, this is plus. This is the voltage VEB. This is the transistor. This is the emitter portion. This is the base terminal. So the current of base is flowing here, IB. This is another emitter. This terminal is the collector terminal. So from here we will calculate the VCB. Okay. This is the collector terminal. So the IC current is flowing from this side. This is minus, this is plus. A voltmeter is connected here. This is V. This is plus, this is minus. Another variable resistor is connected here, potentiometer. Okay, so now we are connected here. So this is like this, it is connected. This is plus, this is minus, this is VCC. And this is R2. And there is the ground. So this is the circuit configuration or circuit arrangement for input and output characteristics curve in CV configuration. Anybody any problem with this? Is it okay? Can you see this? Hello?
Sir.
Okay. So So what I told, this is the circuit configuration or circuit arrangement for input and output characteristic curve in CV configuration. So for the input characteristics, if we talk about input characteristics, what I will see, I will do what? I will relate the input or emitter current IE and input or emitter to base voltage VEB. So IEE, okay, and VEB. So VI, that means voltage is in the x-axis. So it will be VEB, that is emitter to base voltage, VEB versus IE. Keeping output or collector to base voltage constant. Keeping VCB constant. Understand? That is for the input characteristics. So how the graph will be looking like? If you see the graph, how it will look like? So x-axis is our VEB and y-axis is equal to IE. So this is the value 0, 1, 2, 3, 4. Like this value are there, and this is 0.2, 0.4, 0.5, 0.6, 0.7. So VEB will be in bold. Okay. So on constant VCB. So first we will take VCB is equal to 12 volt. Then we will take VCB first 2 volt, 6 volt, 12 volt. Like this we will get. Okay. So you will get like this value. So like this we will get the value. This is for VCB equals to 12 volt. This is equals to VCB equals to 6 volt. This is for VCB 2 volt. And this 0.5, 0.6 is the called the knee voltage. So 0.6 will be called it the knee voltage. Okay. Everybody cleared with this? Hello. Can you hear it?
यस सर क्लियर सर नी वोल्टेज समझा दीजिए सर.
Okay. So what happens in this circuit? This is an NPN transistor. So the series resistor RS is connected to the limit to the emitter circuit. The value of VEB may be varied with the help of a potentiometer R1. So R1 is the potentiometer, will vary the voltage of VEB. The collector voltage VCB is varied by adjusting the potentiometer at R2. So the DC millimeters and DC voltmeters have been connected in the emitter and collector circuits to measure the voltage and the currents. The input characteristics in CV configuration are plotted between emitter IE and the emitter base voltage VEB for different values of collector base voltage VCB. Input characteristics has been shown in this graph. So if we observe, you will see some points there. Below the cut-in voltage or the knee voltage, the emitter current is negligibly small. So you can see the emitter current is negligibly small below the 0.6, that is the knee voltage or the cut-in voltage. After that, Uh, so that is the definition of knee voltage or cut-in voltage. The value of cut-in voltage is approximate, or knee voltage is approximately 0.7 for silicon and 0.3 for germanium tungsten. After the knee voltage, the emitter current IE rapidly increases rapidly with a small increase in the emitter to base voltage VEB. This indicates that the input resistance in CB configuration is very small. Number three, with increase in VCB, the curve shift upwards or become vertical. Hence, RI decreases. RI is the internal resistance. With the increase in VCB, at any point of the curve, what we will see, the value of AC or dynamic input resistance is given as Ri equals to del of VEB. Del means small change in voltage by small change in current with VCB constant. So the dynamic input resistance R1, Ri is very small, nearly 25 to 100 ohm. So Ri ranges okay. Up to this, everybody is cleared. Hello. Can you hear me?
Yes, sir. Clear.
Okay. So that is the input characteristics in CB configuration. Now there will be output characteristics in CB configuration. This is IC versus VCB. For our output characteristics, we will be on the x-axis, it will be the collector to base voltage and versus the collector current. So that is called output characteristics. So here also it will be 0, 1, 2, so like this the value will be there. This is -2, 1, 3, 4, 5, 6. So like this. And you will see the output characteristics curve like this. So this is I equals to 10 milliampere. This is I equals to 8 milliampere. This is I equals to 6 milliampere. This is I equals to 4 milliampere. This is I equals to 2 milliampere. This is I equals to 0. So this is our cutoff region. This is the cutoff. This is the saturation. And this is the active. This is the saturation. And this is the active. So the output characteristics curve in CV configuration can be obtained with the help of same circuit arrangement we have shown earlier. A suitable value of input current, that is emitter current, is fixed. Now keeping emitter current IE constant, collector to base voltage is increased and the corresponding changes in collector current are noted and a graph is plotted. The few points that is followed from this graph are that the characteristics curve show three regions, namely active region, cutoff region and saturation region. In active region, the collector current is approximately equal to the emitter current I. Emitter current increases slowly for the increase in collector to base voltage in active region. Hence, in active region, the curves are nearly flat. This is also means that the output resistance in this configuration is very large. If VCV, that is collector to base voltage, becomes negative, the collector base junction is set in the forward bias, which causes collector current to decrease rapidly. This region is known as saturation region. In saturation region, the collector current does not depend on the emitter current. Next is in saturation region, since collector base junction is also forward biased, a small increase in collector to base voltage results in a large increase in the collector current. Now, if emitter current IE is made 0, then the collector current is not 0. It has a small value. This small value is called the leakage current or ICBO. The curve for I equals to 0 corresponds to the cutoff region. In this region, both the junction and both the junction are reverse biased. With this help of the output characteristics, the dynamic output characteristics tau I R of D, R of 0 can be found by expression R of 0 equals to del of VCB by del of IC with IE constant. Here VCB and del IC are small changes in collector to emitter voltage and collector current in the given for a given point. With the help of output characteristics curve, DC and RC current gains in CV configuration can also be determined. That is, DC current gain DC current gain is equal to alpha DC, that is equals to alpha, that is equals to IC by IE, where IC and IE are the values of collector and emitter currents at any point on the curve. So AC current gain can be written as AC current gain that is equals to AC current gain equals to alpha 0, that is equals to del of IC by del of IE at VCV equals to constant. Where del IC and del IE are small changes in collector and emitter currents around a given point on the curve. So that is for the our what I will tell, that is for our common base characteristics, that is input characteristics and output characteristics. So anybody any problem with this? Any confusion, anybody? Everybody?
यस सर,
Yes, sir.
इमीटर करंट भी मिली एम्पियर में ही होगा ना सर?
हाँ हाँ ठीक है, तो दिस इज द बेस कॉन्फ़िगरेशन, कौन बेस. We are going to the next page. Now we will discuss about the transistor characteristics in common emitter configuration. That is input and output characteristics in common emitter configuration. And the last but not the least, we will discuss about the common collector configuration. So let us write. So let us draw the circuit diagram. So this is the collector portion, this terminal. So here I will take this, I will add a milliampere here, MA. There will be a voltmeter. There is a variable resistance. This is the VCC. This is a plus, this is a minus. This is R2. This is the base terminal. So here I use a microampere. This is a voltmeter connected here. V. This is the base. and this is the emitter. So three terminal device, the three terminals are this. So from this side, we will determine the VBE. This is plus, this is minus. This is plus, this is minus. This is positive, this is negative. Okay. Another potentiometer is connected here. This is the resistance. This is the voltage. This is the base emitter voltage VBE. This is plus, this is minus. This is R1 potentiometer. This side we will assume VCE. So this is positive, negative. This is the ground. This is N, this is N, this is P. Though this is the circuit arrangement for the input output characteristics on a common emitter configuration, C configuration. So everybody understand the circuit? Everybody? Hello? So the input characteristics curve may be obtained with the help of circuit arrangement shown here by increase the base to emitter voltage, that is VV, in steps and recording the corresponding value of IB while keeping VC constant. In figure, the typical input characteristics curves relate IB and VBE for various value of VC. With the input characteristics, we can find out the value of dynamic input resistance of a given point. At a given point, it is given as the ratio of small change in VBE to the resulting small change in IBE, keeping BC constant. That is what? Ri equals to delta VBE by delta IB on VC constant. Okay, clear? So if I draw the graph, are you listening or not listening?
Yes, sir. Listening.
Okay. So if I do the input characteristics, if I draw it, this is IB in the order of microampere, and this is VB in the order of voltage, that is volt. So this is 0, this is 10, 20, 30, 40, 50, 60, 70. This is 0, 0.4, 0.5, 0.6, 7, okay. ग्राफ थोड़ा चेंज होगा. So like this the graph will be, okay. So this is VCE 0 volt. This is VCE 2 volt. And this is VCE 4 volt. Okay. If I take dotted lines, how to calculate I am seeing you. Just a minute. So this point is Q1. Let us name this point, sorry. Let us name this point Q1. I will draw the diagonal on this. Okay. This is Q1. This is Q2. Okay. So another diagonal. Okay, this point is in the middle point, Q1, Q2, this is Q. Okay, so I have done this. Now I will point it. What is this? So this is VBE, delta VBE. And this is what? Delta IB. Understand? Do you understand the graph? Are you there? Anybody? Hello?
Yes, sir.
Sir.
Oh, okay. So like this, you have to calculate in the practical. If you have calculated these things in the practical, then like this, you have to calculate. This is the points, then you have to calculate, and from there you can find out the value of delta V and the value of delta IB, and then you will find the value of uh, what? Input resistance. Now for the output characteristics curve, if I think about the output characteristics curve, let me draw it for you. Okay, so I am drawing the curve. So this is the IC collector current. This will be in the order of milliampere, and this is the VCE. Okay, so IB will be constant here. So this is 0. These are the value 10, 20, 30, 40, 50, 60, and this is 70. This is 1, 2, 3, 4, 5, 6, 7, 8. Okay. Now there will be the graph. So this is the first one. Then this will be the second one. This will be the third one. This will be the fourth one. Okay. Now we have to draw the sampling line. Just a moment. Okay. So it will be like this. Okay. And this will be the saturation region portion. Total this portion is called the saturation region. Okay. Next, this portion is the active region. From here, then it will go down to here. And this is the saturation cutoff region. This is active. This is saturation. And this is cutoff. Okay, understand everybody? Do you understand the diagram? कोई
Yes,
रेस्पॉन्स
sir.
नहीं. ओके, सो यहाँ पर कुछ इंपॉर्टेंट चीज है जो आप लोगों को बताना चाहता हूँ. सो ये है कि आउटपुट कैरेक्टरिस्टिक्स इन सी कॉन्फ़िगरेशन can be plotted with the help of circuit arrangement that is shown above. The related output current IC to the collector to emitter voltage for different values of input current that is IB. From the output characteristics, we can draw a few points. In active region, the collector current increases slowly with increase in VC. Output characteristics in C configuration are less horizontal than those of the CB configuration. This indicates the, that the output resistance is small in C configuration than CB configuration. That is the first thing. Next is, as the values of VC decrease below 0, IC increase rapidly. This occurs due to the reason that when common emitter voltage, that is VC, decrease below to 0, collector to base junction becomes forward bias. This means now both the junction are forward bias. This is called the saturation region. In saturation region, the collector current IC does not depend upon the input current IB. Now, if the base current is made 0, then the collector current is non-zero. It has a value known as reverse leakage current or ICEO. This condition is called cutoff region of the transistor. Next observation is that output characteristics may be used to find the dynamic output resistance at any given point, which is represented by R0 equals to delta VCE by delta IC at what constant? At IB equals to constant. The output characteristics may also be used to calculate the DC current gain beta and the AC current gain B0. So beta equals to, if I write, I can write beta equals to IC by IB and AC, this is the DC current gain. Now AC current gain this can be represented as beta 0 equals to del of IC by del of IB. For what? For VC equals to constant. So this is the common common emitter configuration and the input output characteristics. So I think everybody has noticed it, and I think everybody has understand it. No problem, I think. Now last thing is that what we are going to do is the common collector configuration. Common base is done, common is done, and now we will go for common collector configuration. Everybody, do you understand common emitter and common E?
Yes, sir.
Okay, so let us start the common collector input and output characteristics. Just a minute, give me a time. Just a minute, I will drink some water. Please give me a second. Thank you. Thank you very much for waiting for me. Now let us draw the common collector configuration. So let us draw the circuit. Today is 21. So this is the resistance. This is the VBB. This is the resistance RB, let us name. Voltmeter is connected here. Ammeter is connected here. Across this, I will measure the VBC. This is plus, this is plus, this is minus. This is plus, this is minus. This is the pin, our transistor, NPN transistor. This is the collector current, IC, which is connected to the ground. Here, this is the IB. This is flowing this side. This is the ammeter again. This is N. This is N. This is P. This is the IE flowing this side. This is plus, this is minus. Here is the another voltmeter, V. This is minus, this is plus. Across this, I will okay, this side. This is the resistance. So across this, I will calculate VCE. This is RE. This is minus. This is plus. This is VEE. And this is the collector current, IC. So this is the input-output character configurations. In this configuration, the base terminal of the transistor serves as the input, the emitter terminal is the output, and the collector terminal is the common for both input and output. Hence, it is named as common collector configuration. The input applied is applied between the base and the collector, where the output is taken from the emitter and collector. In common collector configuration, the collector terminal is grounded. So common collector configuration is also known as grounded collector configuration. Sometimes common collector configuration is also referred as emitter follower, voltage follower, common collector amplifier, CC amplifier, or CC configuration. This configuration is mostly used as a voltage buffer. The input supply voltage between the base and the collector is denoted by VBC, while the output voltage between emitter and collector is denoted by VEC. In this configuration, input current or base current is denoted by IB and output current or emitter current is denoted by IE. The common collector amplifier has high input impedance and low output impedance. It has a low voltage gain and high current gain. The power gain of the common collector amplifier is medium to fully is medium, sorry. Now we will configure the input characteristics. The input characteristics describe the relation between the input current or base current and input voltage or base voltage, base collector voltage, that is VBC. The input current or base current is taken along the y axis, and the input voltage or base collector voltage is taken along the x-axis. To determine the input characteristics, the output voltage VEC is kept constant at any voltage, and input voltage VBC is increased from 0 volt to different voltage levels. For each level of input voltage VBC, the corresponding input current IB is noted. A curve is then drawn between the input characteristics between the input current IB and the input voltage VBC at constant output voltage VEC. Okay. Clear, everybody?
Yes, sir.
So what will be the input characteristics? If I draw the input characteristics, it will be as you will be little bit accustomed with this input characteristics. This will be IB. This is in the milliampere. And this is VBC in volt. So 0, 2, 3, 4, sorry, 2, 4, 6, 8, and here 20, 40, 60, 80. So this is VEC equals to 3 volt, and this is VEC equals to 5 volt. So that is the input characteristics. You can see the input characteristics, why it is happening like this. Because the common collector amplifier has a high input impedance and low output impedance. So high input impedance, so there will be no input current flowing like that. So it will be like this straight line. A little bit straight, not little bit like this. Okay, clear everybody? Everybody cleared? Are you there, anybody? Hello? Hello? Hello?
Yes, sir.
Yes, sir.
So you understand that this is the input characteristics. Why it is happening, you understand? Because there is a high input impedance. So I will get only the straight line. There will be no curve. Okay. So what will be the output characteristics? Let us see. So this is 12. This is -1. Okay. So if I draw the curve now, we'll see. Sorry. 1 minute. So like this, the curve will be, this will be the value of IB. IB equals to 120 microampere. IB equals to 100 microampere. IB equals to 80 microampere. IB equals to 60 microampere. IB equals to 40 microampere. IB equals to 20 microampere, and IB equals to 0. Okay. Clear? So this is our cutoff region. This is the active region. And this is the saturation region. So to determine the output characteristics, the input current IB is kept at constant voltage, and the output voltage VEC is increased from 0 volts to different voltage levels. For each level, the output voltage VEC, the corresponding output current IE is noted. A curve is then drawn between the output current IE uh, output voltage VEC at constant input current IB. So like this, the curve is drawn. In common collector configuration, if the input current or the base current is zero, then the output current or the emitter current is also zero. As a result, no current flows from the transistor. So the transistor will be in cutoff region. If the base current is slightly increased, then the output current or emitter current also increases. So the transistor falls in the active region. If the base current is heavily increased, then the current flowing through the transistor is also heavily increased. As a result, the transistor falls in the saturation region. So the dynamic input resistance for this, dynamic input resistance can be calculated like this: Ri equals to delta VC by delta IB, for VEC equals to constant. And the dynamic output resistance R0 can be calculated by delta VEC by delta IE, at IB equals to constant. Okay. So the current amplification factor gamma can be written as del IE by del IB. The current gain of a common collector amplifier is high. The current gain of the common collector amplifier is very high. Understand? Everybody understand?
Yes, sir.
So that is today's portion, that is the common collector configuration is done. So we have done the input and output characteristics of three transistors, that is three transistor operation, that is our common collector operation, common base, common emitter. So three configuration are there. So we have studied the input and the output characteristics of the common base, common emitter, and common collector configuration. And what we analyze from them, the analyze from that the input resistance is very low in CV configuration. In C configuration, it is little bit more, and in CC configuration, it is very high, the input resistance. Then for the output resistance, for CB configuration, it is very high. In C configuration, it is much higher, but not more than CV. In CB, it is like 1 mega ohm, the input output resistance. But in C, it is like 10 kilo ohm. And in CC, it is very low, that is 50 ohm. Near about, I'm telling this is tentative values. Next is current gain. For the CV configuration, it has a value of current gain that is less than unity, near about 0.98. In C configuration, the current gain is very high, 100%, and in CC configuration, that is also high. In voltage gain for CB configuration is very small, in the order of 150. In C configuration, the voltage gain is in the order of 500, and in CC configuration, the voltage gain is very small, that is less than unity. Leakage current. Leakage current for CB configuration is very small, 5 microampere for germanium and 1 microampere for silicon. In C configuration, this leakage current is 500 microampere for germanium and 20 ampere for microampere for silicon. In CC configuration, this is very much large. It is order of 500 microampere for germanium and 20 microampere for Si. So leakage current factor will always give the problem for CE and CC configuration, which is not much problem for CB configuration. And applications, the CV configuration is application for high frequency application. If we want to do high frequency application, we will use CV configuration. In C configuration, we will use for audio frequency application. And CC, we don't do for amplification because there is a very low output resistance and very high input resistance. So, so we will use it for impedance matching. Any type of impedance matching, we will use this type of circuits. Understand, everybody? I think you have understand this three transistor configuration. Okay, and next day we will talk about what is the importance of operating point, what is DC load line, and what is the importance of this load line. Then with stability factor, we'll discuss about the stability factor. Then we will discuss about different biasing circuits. Okay, that is fixed bias, self bias, emitter bias, collected to base bias. We will discuss everything. So, any problem? So, thank you for joining this class. Thank you very much. Have a good day. Have a good day.
Thank you, sir.
Thank you.